Welcome to Quantum Curious, and in today's video, I'm going to start a new topic. So it is all about quantifying quantum information, and the tools we will discuss here will be very helpful in upcoming lectures. So let's start with the outline of today's video. So first, I will give the introduction and motivation behind these tools. And we will discuss one of the tools today, that is the trace distance. And using this, how can we distinguish two quantum states? Either they can be pure states or mixed states. So let's start with the introduction first. So in the previous videos, we talked about how can we distribute keys between two parties called Alice and Bob, our famous protagonists. And we know that we can do this through quantum communication using quantum states. And our condition was that Eve, that is doing eavesdropping, should be ignorant about this key. So first we have to shared key, and it should be hidden from Eve and appears completely random from the perspective of Eve. So it could be done by quantum communication, and it is fundamental of quantum cryptography. So what is all about the ignorance of the Eve? How can we quantify this seemingly uh, quantitative or qualitative, property? So in order to get information from the quantum state sent by Alice, Bob should be able to distinguish them properly through some apparatus and mechanism. But in quantum states, uh, there is nothing like 0 and 1 distinguish. Quantum states can be perfectly distinguishable, they can be partially distinguishable, or they can be completely indistinguishable. But from the perspective of Bob, the purpose is to distinguish the upcoming quantum states partially or perfectly. And we also want to quantify the ignorance of the Eve. Through this, we can evaluate the protocol of the quantum communication that we are using to distribute the key. So in today's lecture, I will discuss one of the tools to distinguish the two quantum states, and the tools that we are going to discuss is called partial trace. So let's start with the trace distance. So our problem at hand that there is a mechanism or algorithm that uses some kind of state, and we call this state rho ideal. But the part of the state is producing some state called rho real because of some imperfection and some default in the smaller part of the algorithm. So how badly is the larger protocol will be affected? So the trace distance measures the trace or the distance or the how the two states are distinguishable. If the trace distance says that there is very small difference between the two states, then we can use rho real without any hesitation. So trace distance is the property through which we can distinguish the state through a best possible measurement. So another interpretation of the trace distance is that what is the maximum probability of distinguishing two states? So consider we have scenario that the machine that we have built is preparing the two states rho real and rho ideal with some probability 1/2. So it is preparing two states with complete randomness. So in order to distinguish two states, we have to apply some measurement. So consider we have two POVMs, that is M real and M ideal, and the average success probability is going to be this. So this is an optimization problem. We have to choose an optimal measurement that can perfectly distinguish between the two states and give us maximal success probability. In either case, the success probability should be equal or greater 1/2. So our optimization problem is given as this. So here is the definition of the trace distance. The trace distance is given as this in its operational form, and M here is a POVM optimal measurement that we are going to employ to distinguish between the two states. And for the computation, we can write it as this, and we will see that how can we derive this expression from the above expression that we saw earlier. And this says that we can calculate the trace distance by only the singular values of these density matrices, or the subtraction of the density matrices. So let's see that we have a goal to maximize this measurement, and we are given this POVM, and the condition on this POVM is that it has eigenvalues that are positive and they lie between 0 and 1, and M is also a Hermitian operator. So first diagonalize the given density matrix. These are the eigenvectors or the orthonormal basis of the density matrix, and lambda j is the eigenvalue. So writing this in that form and using the cyclic property of trace, we can write it as this. So optimal measurement is just the projector on the positive eigenspace of the given space of the density matrix. So in that case, our problem takes the form as this. So we need to just calculate the absolute value of the eigenvalues, or the sum of the absolute values of the eigenvalues of that density matrix. And this is essentially this part. So we have turned the optimal problem or optimization problem to the sum of the absolute eigenvalues. Let's see an example. So consider we want to calculate trace distance between 0, 0 state and plus plus state. These are two density matrices correspond to 0 and plus pure states respectively. So first we will calculate the density matrix, the subtraction of the density matrices, and then we can calculate the trace distance by using just the singular values of the given density matrix. And we have this answer as 1 over square root 2 as our trace distance between them. So these two states are or can be distinguished properly. Alternatively, we can calculate the trace distance by first finding the optimal measurement operator. So first we will calculate the eigenvalues associated with this density matrix. Then we have to form the optimal measurement, that is the projection on the positive eigenspace And then we can solve this trace to find the optimal or the trace distance between the two given states. So density or so trace distance is just a metric. In other sense, it tells us that how the two states are far, how far the two states are in the Hilbert space. So as the normal distance, the trace distance is also non-negative and it is symmetric and it does not change with the replacement of the density matrices, and it follows the triangular inequality, means that the sum of the uh, two distances should be greater than the distance between the 2 points. And it follows the convexity. It means that the mixing does not increase the trace distance between two density matrices. So consider we have two states, rho I and sigma, and we want to distinguish between them. So mixing the one state does not increase the overall trace distance. So it it tells us, in other words, that it only depends upon the given quantum states, not on the weights of these quantum states. So here is another definition, that is epsilon ball around a state. So consider we have state rho, and some states are very close to rho around an epsilon ball. An epsilon here is very small value. So the trace distance between them should be uh, or will also be greater or smaller than epsilon. So these two states are very close to each other and they can be used alternatively as an approximation of each other. And this approximation is very important in state transformations and analyzing errors in quantum information protocols. So in today's lecture, we saw that how can we quantify the distinguishability between the two given states, the quantum states, and we can do it using the trace distance as our quantitative tool of distinguishability. So this uh, you can say tool is very important in quantum information protocols in order to analyze different tasks.